Perfect. We're recording. Okay, good. So today is going to be lecture 4, I believe, and this is continuing our review of orbital mechanics or spaceflight mechanics. And then we won't have an hour and a half's worth of that content today. They're just we'll be finished probably at about the halfway point, a little bit past the halfway point. So then we'll take a break, and then when we come back from the break, we will go over the beginning of attitude representations, which is also useful content. By the end of the day today, you should have everything that you need to do homework 1. And so I would encourage you, if you haven't taken a look at homework 1 yet, definitely now's the time to start on it. If you have any questions, I'm going to have office hours on Wednesday, so we can have a nice long discussion then. We can also talk about it on Thursday. And then I think, I would advise to have seriously attempted everything this week. And then next week is like prime time because it's due on Friday, that sort of thing. And I hope it's okay to have a close of business on Friday deadline because I want you to enjoy your weekend. And I think it would be kind of monstrous of me to keep you like, oh, this is due at noon on Saturday. It's like, try enjoying your Friday night. It's like, no, you have lives outside of this class and I want you to be able to enjoy your Friday. So we're going to keep going with the Friday at close of business deadline unless I get any serious complaints. Also wanted to thank everybody for your feedback in the feedback survey that I gave. It turns out that it actually is anonymous. It was just weird the way that it worked out. I'm still a little bit rusty when it comes to doing surveys on LMS. But overall, it was just overwhelmingly positive feedback. People seemed really happy. Not much in the way of I hate it when you do X, which if you do, like I want to hear it because I want to try to make this as agreeable as possible to folks within reason. But yeah, so if anybody has any other questions, we can field those now, or we can get back to orbital mechanics. And I'm going to pick on somebody to answer some questions about orbital mechanics in a second here. Let me just go ahead and share my screen. We'll just share the whole dang screen. That's what we'll do. All right, perfect. So really quick, can someone just verify that you can see, should say lecture 4, orbital mechanics 2, and attitude representation 1? Is that coming through okay?
I've got it here.
Nice. Okay, sounds good. So I'm going to start lecture with a question. And actually, I'm going to pick on Renee. Are you around, Renee? You want to talk about orbits for a second?
Sure.
Sure. All right. You asked me a great question over email, and so I thought that would actually be a nice icebreaker for today's lecture. So we're going to attempt to answer a question about orbit elements and time in a second. So just buckle up. Here we go. This is going to be fun. So let me pose you a question here. Let's say that this, oh, my drawing tablet going to be my friend right now? Okay. Apologies. I think my computer just needs a second. Okay. Let's say that this is the Earth. And let's say that we have a spacecraft. You know how I like to draw a spacecraft, kind of minimalistic. There it's got the body and the solar panels. And let's say that it's orbiting in a perfect circle. And that's going to be important to answer the question. So it's a circular orbit. And let's say that at some time t1, it's also at theta 1. Okay, theta 1. Remember that theta is what we call true anomaly. And that is basically the angle, we're going to call it the angle from periapsis. And that angle describes the position of the spacecraft. So at some future time, the spacecraft is going to be here, and we're going to call this at some time t2, it's going to be theta 2. Okay, so here's my question. What is the relationship between delta t, change in time, and delta theta? And so Renee, easy version of the question is for a circular orbit, just knowing what you already know, what we talked about last lecture, Could you hazard a guess for how to figure out change in theta given change in time or vice versa?
Um, yeah, I mean, I would go to the equation for, this is probably going to be overcomplicated, but the equation for force for a circular orbit.
Mhm.
But actually, no, we know V equals R omega, and omega is theta dot. So
Wait, hang on.
I'm overcomplicating things.
V equals R omega theta. Okay, so that's absolutely no, that's actually the pretty good way of doing it. So for a circular orbit, your angular velocity is constant, and
Hmm.
that's a pretty good way of handling it. What I was imagining was something which is similar of degree of difficulty, which would be you can find the period of the orbit. There's an equation for that, and if you know how long it takes to clock out 360 degrees, then you could just set up a proportion, right? It's like the
Yes.
yeah, so it takes 45 degrees is what, 1/8 of a full circle, so it'd be 1/8 of the period, something like that. But no, I think I like your answer just as well. So congratulations, you passed, but you're not off the hook yet. This next question is going to be intentionally unanswerable, so don't feel bad. But the question for you and for everybody is, what if it's not a circle? What if it is an ellipse? That's when things get kind of ugly. So suppose we've got this. Got some ellipse. I can do a little bit better than that. There we go. And so close enough. So what if now we have T2 and theta 2 and T1 and theta 1? And then what if we also had some T3 and theta 3? So for an ellipse, now what do we think?
It's going to vary based on where you are. Like,
Hmm. I like that
like
answer.
your
What
radius
what's going to
varies.
vary exactly?
Yeah, your radius is going to vary, and therefore won't your the relationship?
Mhm. So
Yeah.
your distance varies as a function of time and of theta. That
Yes.
also means that your velocity changes as a function of
Yes.
time and of theta. That also means that your angular velocity changes as a function of time and of theta. And that
Hmm.
means that you are always either speeding up or slowing down as you track along an elliptical orbit. And you might have seen depictions of something orbiting something else on an ellipse. Maybe if you look at like GIFs of like a comet circling the sun, it's going very fast at perigee or perihelion or what have you, and it's going very slow at apogee. So you can imagine high kinetic energy, high potential energy, high kinetic energy, high potential energy, something like that. And so, is there a mathematical relationship that we could use to find change in time given change in theta or change in theta given change in time? And the answer is yes. But I wanted to have this conversation to motivate how not easy it is. Like this is not trivial. But thankfully, some people have already thought this through and they have an answer for us. And so that's what we're going to be talking about today. So thank you, Renee. I think that was a good kind of warm up conversation for everybody. And you're officially off the hook, so you can relax now. Okay, so what we want to do, and I'll just write this out here. These are my notes. We want to write theta as a function of time or vice versa for an elliptical orbit. That's what we're after. But theta dot is not constant. Brown. So, anybody who's feeling brave or maybe has already heard this story, what is the name of the scientist who figured out the relationship between delta theta and delta t?
Is it Kepler?
It is very good. Johannes Kepler was the scientist slash mathematician, what have you, who figured this out. And so the equations that we use are called Kepler's equations. And so that's what we're going to be talking about today is Kepler's equations. So Kepler observed, and this is huge. Like this is earth-shatteringly huge because this is the basis of Kepler's equations and the basis of a lot of orbital mechanics. Kepler observed that theta sweeps out equal ellipse areas in equal periods of time. What does that mean? Let's visualize that for a second. It's difficult to overstate what a big deal this is. So let's say you've got some orbiting body on an elliptical trajectory. And let's say that we're looking at this region here. We're going to call this A1, and we're also going to call it delta T1. And then let's look at some other small sliver out here. And we're going to call this A2 and delta T2. So what Kepler noticed was that if the area of the ellipse swept out from one position to another is the same, like the change in area is the same, that means the change in time is the same. And that is the key insight behind Kepler's equation. So we're about to do some fun ellipse geometry, but it's all based on that one insight. And so that's what we're going to be discussing today. So for a circular orbit, we're going to use the Rennes method. So r theta dot squared is equal to mu over r squared, which means that theta dot circular is square root of mu over a cubed. And so that's exactly it. It's a constant angular velocity, nice and simple. For an elliptical orbit, it is a nightmare and a half. And so our strategy is this. Map an ellipse onto a circle. Do our analysis there. And then map back again. That's going to be our strategy. If we can turn an ellipse into a circle and then do math on the circle, then turn the circle back into an ellipse, that's going to be our kind of our whole strategy here. And so we're about to see some diagrams, which usually my artwork is forgivable, but in this case, I truly need to get this one right. So I'm going to kind of do this nice and slow and take my time. So we're going to have crosshairs here. And let's say that we have an elliptical orbit, which looks like this. Okay. And then let's say that we also have a circle. Looks like this. Might technically still be an ellipse, but you get the idea. Close enough. Okay. So if this is one of the foci of the ellipse, and then I guess there's another one over here, but we don't care about that one too much. Let's say for a moment, and can I wonder, how easy is it to zoom in on this? You gonna let me do that? Yeah. Let's just live in here for a little bit. So let's say that we've got a vector coming up this way, and we're going to call that r. This is going to get a little tight, so just bear with me for a second here. And then this would then be theta. Okay. And so then maybe I'll even try a different color for a second. Can I do maybe like orange? Would that work? Yeah. So this orange area here, we'll use that for a second. We're going to call that AE, the elliptical area, if that makes sense. Now, what we're also going to do is we're going to draw a vertical line up from the position wherever the spacecraft is right now. And at this new intersection point, we're going to draw a line down to the center. I can do better than that. Let's make this a straight line. Thank you. Yes, okay, got it. Thank you. All right. Wow, apparently I can't do better than that. All right, third time's the charm. Bear with me here. Ordinarily, I would just kind of fudge it, but like we really do need to get this diagram right. Okay, good enough. Good enough. All right. So we're going to call this angle here capital E, for like an elliptical reference angle, right? And we're going to say that this distance here, and then we have some smaller distance here. So this smaller distance is r cosine of theta. And hopefully that's pretty straightforward from what we're looking at. So r is this vector, r cosine theta is the projection of the vector onto the x-axis. So this little distance there is r cosine theta. This other distance here is a cosine of e, which should also make sense, right? So you've got the semi-major axis, which scales it, and then cosine of e is just the projection of this angle onto the x-axis, right? Okay, so then what we're going to do then is we're going to map this over onto just the circle. So bear with me for a second while I draw. Ooh, I can do better than that. There we go. I'm going to draw just a circle. And those of you that have taken spaceflight mechanics have probably seen this all before, but it doesn't hurt to get a refresher. All right, good enough. Maybe I'll scooch this over a tiny bit here. There we go. And so here's my attempt at a circle again. Hope we all are following along okay at home. And good enough. Okay. So we're going to keep this same angle E. And then what we're going to do is we're going to say this is the same focus F. We're going to draw a vector down here. And I'm going to color code this. And hopefully what you can see is that if you took the ellipse and you grabbed it at the top and you grabbed it at the bottom and you stretched it into a circle, this yellow area AE would become this yellow area AC. That's kind of the point I'm trying to get across here, where this angle is still E. Okay. And this distance here is A times E. And this distance here is the radius of perigee. And this distance here is A. All right, so far so good. So here is one of the key insights. So just to be clear, once again, we took our orbit. We're looking at the area. Remember, if we go up here, we're looking at different areas swept out. And if we take the area traced out over a certain duration of time, and we just grab this ellipse and stretch it into a circle, we get this AC. And the relationship between AC and AE, I'm going to zoom back out again here. Zoom in a little bit. Get the original zoom back here, one sec. That'll do. So the relationship between AE and AC is actually an extremely simple one. It's just a linear scaling. So A ellipse is B over A times A circular. You're just scaling by the semi-minor axis and the semi-major axis. And then the key insight here is that the derivative of the elliptical area with respect to time is constant. Okay, that's kind of what we were saying before. But the change in the area swept out over time is a constant over time, if that makes sense. So just to add a few more definitions in here, AC is, you could think of it this way, right? If you wanted to find this area AC, it is the area of a wedge, hopefully you can see that, minus the area of a triangle. It's like those high school math questions or those SAT questions where it's like, here's this weird kind of shape that's made of the intersection of a circle and a square. Find the area. And it's like, well, in this case, if we want the yellow area AC, it's this wedge minus this triangle. And that gives us kind of what's left over. Okay, so let's kind of formalize that a little bit, right? So the area of the wedge is going to be like this, 1/2 a squared e. And the area of the triangle is going to be one of those 1/2 base times height things, right? So the base is a little e, and then the height is a sine of e. So what we did was we just took the area of this wedge and we subtracted the area of the white triangle. We got the remaining yellow area, which is AC. Okay. We also know that AE, the elliptical area, the one on the left, is B over A times AC, which means it's B over A. Actually, we're going to clean this up multiple steps at once here. It's actually going to be 1/2 A B, and then in parentheses, E minus E sine E. And I think I made a mistake here somewhere. Hang on, did I? 1/2 A squared E. Yes. Nope, actually, wait. No, that checks out. I like it. Never mind. So far, so good. So then we know, bear with me for a second here, that dAdE is constant, right? So dA dt is constant. And we can think of this as the area of the ellipse divided by the full orbit period, right? So the ratio, we know that we trace out equal amounts of area in equal amounts of time, and that ratio is a constant. That means that you could just consider it as the full area of the whole ellipse divided by the full orbit period, which is what? Well, we know a full ellipse is pi, semi-minor axis, semi-major axis, reverse those two. And then we know the orbit period, we talked about this last class, is 2 pi square root of a cubed over mu. And so those pi's are going to cancel out. And so what that tells us is that dAe is going to look like this. AB over 2 square root of mu over a cubed dt. Okay, you might already be able to guess that some calculus is about to happen, right? So we can say, after a bit of integration, that AE is the integral of all this. And now, what's the integral of AB over 2? Oh, yeah, here's some calculus for you. AB over 2 square root of mu over a cubed. It's ugly, but we can do it. Dt, but it's going to be the integral with respect to time, right? So it's going to be the integral from some initial time to some final time, which we're going to write like this for now, of AB over 2 square root of mu over a cubed dt. All right, so we're going to pause for a second because it's been a lot of math all at once. Who's feeling real brave about calculus and wants to try this integral? Or maybe you can intuit that actually this is a trick question and it's a very easy integral.
I'll try.
All right, what do you think?
Well, there's no t's in the integral, so that could just be a constant. So you just add a t.
Yep, or actually, because we need to do fundamental theorem calculus, there's, t minus t naught.
Oh, right. So it's t minus t naught.
Exactly, but you basically got it. Yep, very good. So yeah, so you can, I'm glad that you were brave enough to try that, because it's actually super duper simple. It's AB over 2 square root of mu over a cubed. All of this factors out of the integral, and then it's just the integral of dt from t to t naught. So it's going to look like this. Very nice. Okay, So we're still not quite done yet, right? So what did we just say? We said that AE is all of that, okay? But we also know that we can say, all right, AE is this. So here, I'm going to take this whole thing and I'm going to call this right-hand side. And I'm going to take this whole thing and I'm going to call it left-hand side. And we're going to combine those now. So 1/2 AB E minus E sine E is equal to AB over 2 square root of mu over A cubed T minus T naught. Interesting. Okay. Cancel, 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 cancel. And we arrive at something that ought to look a little familiar. E minus E sine of E is equal to the square root of mu over A cubed T minus T naught, which is, go back to drawing. We're going to do a red pen for the marker here. This is Kepler's equation. All right. So are we ready to declare victory yet, or is there more work? This is Kepler's equation. Use EQN, where everything on the right-hand side of the equation is sometimes referred to as mean anomaly. There we go. Okay, are we done? Let's scroll back up because we just did a bunch of math, a bunch of stuff happened. We want to write theta as a function of time for an elliptical orbit. Well, we got time in there. There's no theta. Okay, fun. So we're actually only half done. But in the interest of brevity, because this is not an orbital mechanics class, this is a navigation class, I'm going to present the other Kepler's equation to you without derivation. And I'm going to hit you with another one of those exercise left to the reader deals, because you can actually, from a little bit of kind of, ellipse and circle geometry, you can convince yourself that this is the case. But what we need is a relationship between theta and E, and that is this. The tangent of theta over 2 is equal to the square root of 1 plus E over 1 minus E times the tangent of E over 2. And if you felt like proving that to yourself, it's not too tough. Also, if you took spaceflight mechanics at RPI, you've definitely seen the full derivation. You could go back to a textbook. Howard Curtis textbook is totally fine. So this is the other Kepler's equation. And you need both. You need both. And so our procedure is, if you know theta, if you know the change in theta, right? What you can do is, let's see here, actually, be careful that I don't lead you down the wrong path. If we know theta can give us some information about E, and E can give us some information about T minus T naught. The thing is, we can't really know what time it is. We can just know T minus T naught, and it is of critical importance that T naught is time of periapsis. T minus T naught is time since periapsis. So all of this is based on counting seconds since periapsis. So you can't do this equation willy-nilly to find some delta t as a function of some delta theta. You'd actually need to do it twice. So you would need to plug in some t plug in some theta to find the time since periapsis of that theta, and then plug in some other theta to find the time since periapsis of the other theta. So that's kind of a operational concern. So we do need to keep that in account, that the relationship between theta and t, it's the time since periapsis gives you the, you can think of theta as the angle since periapsis. So we're not directly mapping t onto theta. We're mapping change in time to change in theta. So that's it's something to just be careful about. And then while I'm busy dumping equations on you without derivation, I'll also mention that for hyperbolic orbits, aka the other type of orbit, again without derivation, but in case you ever need them, we have this square root of mu over a cubed t minus t naught is equal to e hyperbolic sine of some angle f, which kind of plays the same role as e. And then we're going to have another equation which looks like tangent of theta over 2 is equal to the square root of 1 plus e over e minus 1 hyperbolic tangent of f over 2. And so instead of our eccentric anomaly, which is e, so actually I might even mention that, e is the eccentric. This is the hyperbolic anomaly. And why not use capital H? Great question, asked Kepler, but that's basically it. So here we have Kepler's equation, the other Kepler's equation. We can use these to go from theta to t, or we could use these to go from t minus t naught to theta, or in this case to e, and then to theta. Now, what you might notice is that things get a little bit ugly. There's a couple of other concerns, right? First of all, we have e, which is an angle existing not inside of a sine function or a cosine function. So it's absolutely critical when we're doing math with this that we use radians, because you're not allowed to have what you might call a naked angle, an angle that's not inside of some operation like a sine or a cosine. You can't do that with degrees. It absolutely has to be radians. So I just want to make that point. The other concern is, it might or might not be obvious at first glance, that this equation is quite a lot harder to solve in one direction than it is to solve in the other direction. And it comes down to this first Kepler's equation. If you know E, then t minus t naught is pretty trivial to find, right? E minus e sine e, compute the left-hand side, you can compute square root of mu over a cubed, and you can divide it out, and then you get t minus t naught. If you know t minus t naught, and you know mu, and you know a, and you know little e, finding big E is pretty annoying. There's actually no closed form solution to Kepler's equation. You're forced to do some sort of a iteration or some such. And there's details if you go check out any undergraduate textbook about solving Kepler's equation. There's details on how to solve it in not necessarily the optimal way, but a very simple and easy to understand way. Solving Kepler's equation in fewer computations is something that people are literally still thinking about. Like, that's not a completely settled debate hundreds of years later. But so anyway, that is enough about Kepler for now. I think I've bothered you plenty. I think I'd like to move on to our last topic within orbital mechanics, unless anybody has any questions they want to do a go back.
I'm a little bit confused. This is probably my lack of background.
Mhm.
But little e here, is that the eccentricity that we talked about last time?
Yes.
Okay, and then when you went to the circle map with AC, the wedge,
Uh-huh.
you've got a length, just a little e.
Yep.
Wasn't okay, and that's just a times the eccentricity.
Yep.
Okay, thank you.
Yeah.
Sorry.
No, totally fine. And I recognize, especially if you haven't seen this before, or if this is your first time going through this is going to feel like a lot. So don't expect this to all click and make sense the first time. Like this is the 100th time I've seen this, so I'm kind of blowing through it. But give yourself some time to kind of chew on it a little bit. The derivation is great, and I think it's important to understand derivations, but the key thing is in red here is these equations, which are tools to let us map from theta to time since periapsis or back and forth. And I think as you start to attempt the homework and use Kepler's equations to propagate the orbit, so you can essentially, using what we've discussed now and what we're right about to discuss, you can use Kepler's equations to propagate an orbit. You can say at 5 minutes from now, what is the new theta? Well, you can answer that question with these equations. And then if you have the new theta and you have all the other orbit elements, you can go from orbit elements to position velocity and vice versa. And so from a tool standpoint, this is super duper useful for solving homework 1. You're definitely going to need it. If it takes a little while to make sense, that is a-okay. And then the other big tool, which we're going to talk about today, is orbit elements. And then you're officially ready to start down the path of homework 1. Any other Kepler questions? Cool stuff. Okay, we're going to keep moving then. So the last thing we're going to talk about is orbit elements. And believe it or not, we're actually almost done talking about orbit elements because there are 6 of them, and we already understand 3 of them, and the final 3 are the easiest ones, in my opinion at least. And so let me start with another question. So I'll either take a volunteer who hasn't gone yet today, or well, actually, you know what? We're going to pause for a minute. I'll need a volunteer in a minute, but not right now. So let's say that you've got some position R, which we could think of as R1, N1 plus R2, N2 plus R3. Oh, I almost put a hat on R3. R3, N3. And let's say that you've also got some velocity V, which you could think of as some V1, N1 plus V2, N2 plus V3, N3. Okay. This is 6 pieces of information. R1, R2, R3, V1, V2, V3. So what we would like a more intuitive 6 parameter representation. Because if you tell me V2, the y component of your velocity in the inertial frame, that tells me absolutely nothing about the shape of the orbit. Or if you tell me R3, the z component of the position in the inertial frame, that tells me absolutely nothing about the orientation of the orbit. So what we would like to do is to be able to go from 6 pieces of information, R1, R2, R3, V1, V2, V3, to 6 numbers that describe an orbit more intuitively in a way that kind of works with your gut, basically. And so that's what orbit elements are. Orbit elements are 6 numbers that describe an orbit. And so it is officially time for our volunteer, somebody who has not spoken up yet today and who's feeling brave. Or we could do the dice thing, but I feel kind of sadistic when I start rolling dice. I'll take someone feeling brave.
I can.
All right, let's give it a try. And if you already know the stuff, then this is going to be real easy, but we'll see. So let me ask you this. How many degrees of freedom? How many
Oh, like
degrees of freedom? Bear with me for a second. How many degrees of freedom does a 2D ellipse in 3D space have?
well, I mean, you got 3 for like the location,
Mm-hmm.
and then I guess do you have 2 for just like the size of it?
Yep.
Um,
And we're almost done. So you've got, I'm going to put it this way. There's the position of the focus. That's what you were saying, right? The position of the focus.
yeah.
Which is 3 pieces of information. And then you've also got shape, which is 1 piece of information. And you've also got size, which is another piece of information. Or you could describe size using 2 pieces of information. It gets a little bit how you feel like defining it. There's one.
Yeah, I was describing it as like how tall it is and how wide it is. With, like,
Yeah, so you could use
yeah.
A and B. I'm getting ahead of myself, but those are some of them. You could use A and B, gives you how tall it is and how wide it is. Or you could use A and E, gives you how wide it is and how elliptical it is. It's kind of,
Okay, yeah.
whichever one you feel like using that day, right? That sort of thing. We're not quite done yet. Is there anything else we don't know?
The angle that it is.
The
I
angle, and
guess.
how many angles?
I mean, I think that would be 2.
Almost. So think about it this way. The ellipse that's floating in 3D space can have any orientation in 3D space. How many angles do we need to describe any orientation in 3D space? It's not two.
That would be 3 then.
Three. Very good. Very, very good. Excellent. So what we have here is there's 1, 2, 3, 4, 5, 6, 7, 8 degrees of freedom in a 2D ellipse that is in 3D space. However, we can cheat. We know the focus is at the two-body center of mass, right? So if you're orbiting the Earth, it's like, well, you know, the center of mass of the Earth and the spacecraft is the Earth, right? Like the spacecraft is so small. So the position of the focus is something we don't really need to worry about. So actually, we're happy with 5 numbers: shape, size, orientation. But then there's one secret other one, which I kind of left out, which is the position of the orbiting body. So, Merritt, if you still have any gas in the tank, or somebody else, how would we describe, how many degrees of freedom is the position of the orbiting body?
Like the spacecraft itself.
Yeah, what's the position of the spacecraft? How many degrees of freedom does that have?
I mean, that also has the like it has 3 for where it is, and then
So
3
three is the obvious
angles.
answer. 3 is the obvious answer, but we can cheat. We can cheat a little bit because here's the thing. Let me scroll up. You know that you're on an orbit, right? So if you already know the shape, size, and position of the orbit, you already know, like, it's constrained to be flat. So, you know, we've dropped 1 degree of freedom right there, because its position in the parafocal frame is going to be two-dimensional, right? X and Y, instead of like R1, R2, R3. But actually, it's even fewer degrees of freedom than that. You want to take a stab at it?
I mean, would you just do R and theta to describe it, I guess?
Even better, but there's one further step. You're so close. I love the way you're thinking about this, though. Do we really need to know R? Because remember, if we go back to last lecture, we scroll through our notes, R is a function of theta. If you know the angle that you've clocked out, you can actually compute the distance. So there's only 1 degree of freedom, and it's theta. We already know theta. So the position of the orbiting body, which is one piece of information, is theta. There we go. So you're working too hard because we put in all the effort to describe the shape, size, and orientation of the orbit. We actually get the position kind of like almost for free. Like we only need 1 parameter to describe the position, and then everything else kind of falls out. But anyway, excellent job on that. I'm very, very pleased with your thought process, and clearly you have not fallen asleep, even though it's probably after dinner time. So thank you, Merritt. That was good. So to be more clear about what we're talking about now, shape is E, size is A, and orientation is 3 new ones that we haven't learned about yet: big omega, I, and little omega. And if you look at all of this, this is 6 degrees of freedom. So we're going to talk briefly about what these 3 angles mean: big omega, I, and little omega. But what I would posit to you is that there is now 6 pieces of information, R and V, or 6 pieces of information, theta, E, A, omega, I, omega, and that there must be some straightforward mapping between them so that if you know one, you know the other, and then back and forth, that sort of thing. So we're going to get into that in a moment. I think we've been talking for long enough. It's been about 45 minutes. So why don't we take about a 5-minute break? So I'm going to take a break. Of course, for me, it's 6:17. For you, it's 7:17. So we're going to say back at, what do we think? Maybe 7:23. Give you like 6 minutes. So take a break, go to the bathroom, get a glass of water, whatever you got to do, and we will continue our discussion in a bit.
Hey, Professor.
Yeah, what do you got for me?
Oh, Is it okay to, sorry, not Professor Paul.
There you go. I
Sorry,
was about to correct you. Good job.
sorry about that. Is it okay I ask a question during
Yeah,
break?
what do you got?
I just make sure I'm not confusing myself. A is the semi-major axis.
Yep.
Okay, thank you so much.
Yep. And what Merritt was getting at earlier was you could use, and this is kind of where, people hundreds of years ago decided it's theta E A omega I omega. But you could also use A and B instead of E and A, right? Because A and B, actually, we're going to go back to, this is what happens when you ask me a simple question. You get a complicated answer. Bad. Where is it? Here it is. You see how you could use A and B to describe the shape and size of the orbit?
Yeah.
Or you could say E gives you the shape and then A kind of gives you the size. Because if you know A and E, you can compute B. If you know A and B, you can compute E. You could also use H. So H, which you get really easily from, H is just R cross V. The specific angular momentum h actually also tells you the size of your orbit, but in a different way. And so some people will use EH theta omega I omega. And then also what we're going to see in a minute is that omega I and omega are totally arbitrary, and you could have used 3 different angles to describe it. Just, a famous mathematician who I'm going to have you guess the name in a minute decided that it would be these 3. That's basically it. But anyway,
Okay.
does that help? Feeling good, Kelly?
Yeah, for sure. Thank you so much.
But because you asked me a question, now I get to ask you a question when we come back from break. So
All right.
get ready.
Thank you.
All right, I think we're going to start back up in a minute here. Let's see. All right. So, Calvin, you volunteered yourself to answer a question because you had the audacity to ask me a question. Now, we can't have that. Um, I'm going to ask you simple one, and if you get it wrong, this is a Snapple fact question, so it's totally fine. Do you want to take a crack at what mathematician first thought out these three angles, omega, I, and omega? Somebody who's famous for angle stuff.
Uh, I think a good guess would be Euler. I can't pronounce Euler.
Some people say Euler, some people say Euler. I say you're correct. That is the right answer. Very good. Excellent. So I pronounce it Euler, but don't feel compelled to do the same. And so essentially, Euler was actually doing some math to look at the motion of a spinning top. So you can imagine the spinning top has some axis that it's spinning about, and that axis has two angles that describe it, and then it's got the motion about the axis. And he decided to use a similar mathematical framework to describe an orbit. And here comes one of the more complicated visualizations in this class. So once again, bear with me. I'm going to try to get this right. So what I'm trying to show here is this is the world frame. Okay. And then this is some orbit. And the point that I'm trying to make is that the orbit frame and the world frame don't need to be related at all, right? So we're going to call this N1, N2, and N3 for the world frame. And let's say that the point of closest approach is right here, which is P. So we're going to call this the P direction, which we know is also the direction of the eccentricity vector. And then we also are going to say that there's some line here, and I'm going to draw it like this. And this is the line where the orbit intersects the N1, N2 plane, if that makes any sense. So there's going to be some vector coming out this way. And we're going to call this eta, the ascending node. So you can imagine as your spacecraft is orbiting and it's kind of coming from off screen onto the screen here, and then it's orbiting around, and then it leaves out this way, right? That right here is the point where it ascends from below the N1, N2 plane to above the N1, N2 plane. So, Calvin, sorry, you're still on the hook. Want to take a wild guess at what this node might be called if this is the ascending node?
The descending node.
Very good. Yep, I'm going to throw easy ones at you, but there's going to be a bunch of them, so stand by. All right. So now what we're going to say is, okay, there's some angle between N1 and the ascending node, and we're going to call that omega. And the way that we measure, those of you that have taken astronomy, the way that you measure angles from the x-axis is called a right ascension, right? And so big theta is the right ascension of the ascending node, which is a mouthful. Some people write RAAN, which I would if there was more room. Okay, great. So then the next degree of freedom is the angle between the, basically describing the relationship between the two planes, right? So imagine that there's some angle here which describes the amount that the orbit plane is not in the N1, N2 plane. And we're going to call that angle I. And actually that angle comes up again. If we decided to draw a vector here, which is the orbit plane normal vector. So remember, this is the W hat that we saw all the way back in our discussion of the parafocal reference frame coming out of the page. W hat looks like this. And this angle also pops up here. So the angle between your orbit normal and the Z direction in your world frame is called I, which is your inclination. So you can imagine that a 0 degree inclination orbits around the equator of Earth, a 90-degree inclination orbits over the poles of the Earth. That's basically how we can think about it. And there's one more angle here. And actually, we'll do it this way. So let's say that there is a spacecraft at this location, right? What is the angle here? Still Kelvin, but I'm going to throw an easy one at you. The angle between the spacecraft and the P vector, or we could think of this as the point of perigee. What's this angle? We actually already know that one.
The true anomaly.
True anomaly. Very good. That's theta. And then there's one more, and that looks like this. It's the angle between the ascending node and perigee. And we're going to call this little omega. And little omega is the argument of perigee. Which is funny because when you're talking about orbiting Jupiter, they don't call it the argument of perigove. They don't call it the argument of perigee. Sometimes they'll see argument of periapsis, but I typically see argument of perigee. Just to be thorough, periapsis. But yeah, that's typically how we see that written. And so these are the three angles, and I want these to make intuitive sense. The ascending node describes the intersection of the orbit plane and the world frame XY plane. And that ascending node, by definition, is going to have some angle that describes its location, and that is the right ascension of the ascending node. The next angle is your inclination, which is how much your angle, your orbit is kind of tipped up or tipped down. And then omega is how far away from the ascending node is your periapsis. And that's basically that. So here's everything all in one diagram. And so you can imagine that theta plus omega is the angle of spacecraft from your ascending node, which actually this should have a little hat on it. There we go. And we can also say that the N3 direction crossed with the omega direction is your ascending node, which kind of makes sense, right? The cross product of your orbit plane, or sorry, your world frame Z direction and your orbit frame Z direction is the ascending node. It's the kind of line of intersection of the two, right? And so you could think about it this way, right? Let's assume that we wanted to build an attitude transformation matrix. And we're going to talk more about those in a minute. Actually, this is where I was kind of, when I was designing this class, I was deciding, do I want to go over attitude parameterizations before orbit elements or after orbit elements? And it's kind of a catch-22 because whichever one I do first, the other one would have been nice to have known first. And so now we're about to run into rotation matrices and direction cosine matrices, despite the fact that we haven't talked about those yet. Hopefully you've seen these in another class. If not, then just bear with me for a moment, right? If you wanted to go from the inertial or Newtonian or world frame to the parafocal frame, what we're going to do is rotate omega about N3. Then we're going to rotate I about some new frame. I'm going to bear with me for a second here. Actually, it might make more sense if I write it out this way. Let's do this. If we take the inertial frame and we rotate some amount omega, what this is going to do is we're going to create a temporary A frame. And what you can imagine is if the two frames were aligned to begin with, and then you crank it around, the A1 direction is along the ascending node. Okay. So then we have A frame, and we say we're going to rotate some amount I about A1, which is really the same as our ascending node. That's going to give us a temporary B frame. And then finally, if we start at the B frame, you can imagine that the B3 direction, which was originally the A3 direction, which is originally the N3 direction, that's the B3 direction has now clocked over to be basically the W direction. And yeah, going to take a little bit of time to chew on that for a minute. So we're going to rotate omega about the B3 direction, which is really the W direction. And then we land at the parafocal reference frame. I feel like this bears repeating because this is confusing and I might not have made the most sense out of this, but imagine that you've got some frame that you can twist around with your hands. First, you hold it constant about the N3 direction and you spin it so that your X direction is pointed along the ascending node. Right? Then you hold the ascending node constant and you spin it about the ascending node so that your up direction is pointed along the W direction. And then you hold the W direction and you spin about the W direction so that your new X direction is clocked all the way over to be the P direction, right? So that's your series of 3 rotations. And spend some time, if that doesn't immediately make sense, and convince yourself that that series of rotations will turn your inertial frame into your parafocal frame. And so that procedure is how we're going to build the rotations between these, right? So if T A to N, other way around. If T N to A describes that first rotation, T November alpha describes the first rotation. This is the rotation where we rotate about the N3 direction some amount theta, and we're going to say this is cosine of big omega, sine of big omega 0, negative sine of big omega, cosine of big omega 0, 0, 0, 1. And then next, the rotation from the A frame to the B frame, which is basically rotating about your X direction some amount I. Well, that's going to look like this: 1, 0, 0, 0, cos of I, sine of I, 0, negative sine of I, cos of I. And if me writing this makes absolutely no sense and you're like, where are these matrices coming from? We will discuss that in our very next lecture. So just bear with me for a little bit. T getting from the B frame to the parafocal frame, which describes our third rotation, is going to be rotating about the new Z axis, some amount omega. So we're going to write cosine of omega, sine of omega 0, negative sine of omega, cosine of omega 0, 0, 0, 1. And so if you put all this together, then the attitude transformation matrix that takes us from the Newtonian frame to the parafocal frame is the same as we need to do all 3 rotations. So we start at the Newtonian frame and we go to A, then we go from A to B, and then we go from B to parafocal. And if you multiply this out, this equals some ugly mess. But it gets us back to this matrix, which I'm going to write out for now. P1, P2, P3, Q1, Q2, Q3, W1, W2, W3, or I'm going to write this as T11, T12, T13, T21, T22, T23, T31, T32, and T33. And so I'm going to tab away for a second, but I'm coming back. This should look a little bit familiar because it is this matrix, the parafocal reference frame. So remember, if we can write the p direction, which is just the normalized e vector, and the w direction, which is the normalized h vector, and then q is the cross product of the two, we get this matrix. It's the same matrix, right? So you can arrive at it if you know the orbit elements. You can actually do this whole multiplication and end up at this matrix. Or if you know R and V, you can go, okay, we're going to go from R and V to find H, and we can find E, and then we can find this matrix the other way. So this matrix is kind of the node that we're approaching from either direction, right? You ultimately get back here. Now, if you knew this matrix and you wanted to find the orbit elements, I'm going to show you the equations without derivation because they are, it's not good. It's a little bit messy. But so here's where the equations are, and we can talk about why this is the case if you want to. For now, without derivation, your inclination is simply the inverse cosine of T3, or you could think of it as the inverse cosine of the W3 direction, right where this W3 is this W3. The little omega is atan 2, or the arctangent of T13, T23, which is the same thing as atan 2 of P3 and Q3. And atan 2, if you haven't seen that before, is just arctangent written in such a way, like if you were doing this in MATLAB or Python, it's a means of being careful, like your quadrant check is built into atan 2. So you could just think of this as inverse tangent, but it's a function, right? And then finally, we have big omega, which is atan 2 of T31 negative T32, which is the same thing as saying atan 2 of omega 1, and, or sorry, not omega 1. This is W, right? So this is the W from this frame here. So W1, W2, W3 give you 2 of the orbit elements to begin with, which should make sense, right? I and big omega really just give you the orientation of your orbit plane normal vector. And then little omega tells you how to clock around that to describe where your perigee is, or your periapsis is. That's why it's the argument of perigee, right? And so what this means is, and this is what you can do now, right? Knowing everything that we've discussed, we can now, and I would urge you to consider this here, we can now go from R and V to theta A E omega I and omega. And we can also go from theta A E omega I omega to R and V. You can do both now. And I would say you will want to write functions in MATLAB or Python or whatever you like to do this to help with your homework. All right. And that's it. That is our review of orbital mechanics done and dusted. So we might just take another little break and then we'll dive into the next subject. But I feel like this is a great natural stopping point if anybody has any questions.
Can you scroll back up to where you defined P, Q, and W?
Yes. PQ. Oh, that would actually be. You're talking about back here? Or are you talking about
Yeah,
the
there.
diagram? The first one here, or we have.
Right there. Wait, yeah, there.
Yes. Okay. Yep. So there for a minute. So just as a reminder, P is kind of like the x direction of your parafocal frame. It tells you the direction from the central massive body to the point of periapsis, which is the point of closest approach. Q is just kind of the y direction. It just needs to be there to complete the right-handed frame. W, which has more physical meaning, is your orbit plane normal direction, which is sticking out of the page as viewed here. So if we go back really quickly to this diagram, you can see the P is kind of shooting off in this direction, the W shooting off in this direction. Q isn't drawn because it's not super important for this analysis. Really, P and W are the important ones. But so that kind of gives you an idea. Here, P could be any which way, and we can describe the direction of P and the direction of W using these three angles, big omega I and little omega. Right? Any other questions about the orbital mechanics stuff we've discussed today?
At the bottom where you wrote big omega equals atan of T31 negative T32, should that be atan 2?
It sure should have been. Thank you. I specifically made that mistake on purpose to see if anybody was paying attention. Thank you. In general, only listen to me when I'm right. That's a good rule of thumb. Okay, good. And actually, now that I'm thinking about it, so we are well over our usual class time. Folks are probably getting pretty tired. Why don't we just call it quits for today? It's a little bit of a shorter lecture, but it's fine. And then we'll start off on Thursday with attitude representations, and that'll be like a clean break. So I'm actually going to change the name of this to Orbital Mechanics 2, and we'll just stop there. So maybe I'll rename it so that, because I'm, let's see, review of orbital mechanics part 1, so I'll do that. Orbital mechanics part 2. So with that decision, class is dismissed. If y'all are done, you don't have to stick around any longer. If you have any questions, if you want to talk about homework 1, if you're feeling shell-shocked and you just want to kind of try to make sense of what we just talked about, then feel free to stick around. Otherwise, I think I'm going to stop the recording, and y'all have a great rest of your day. And thanks for being flexible with your schedules.